All right, welcome back. So I'm hoping that after that last assignment, which was really meant as just a quick way for you to build a circuit and then quickly measure stuff like current and looking at voltages across one battery or two batteries, or looking at the voltage drop across, one light bulb or, a series of light bulbs, and just sort of looking at the trends or the patterns that are starting to emerge when we start hooking up batteries in a row or looking at hooking up more and more loads in a circuit. That's what today is all about. We start looking at something called resistance, and we're going to start looking at different ways of hooking up loads and batteries. So we look at resistance as being any situation where we see the slowing down of current flow in a circuit. Now, there are many different sources of resistance in a circuit. Now, we've looked at these things called loads, which are basically devices, light bulbs, motors, heating elements, whatever, speakers, anything that uses electricity and converts it into another form of energy. That is a load, and loads will resist electricity because that is the result of this energy, this electrical energy being converted to another energy. That slows down electrical current. So as a result, loads are places where resistance will take place. But that's not the only place where resistance can happen. Resistance can happen in conductors that are too small for the amount of current trying to flow through it. So if I have a lot of current electricity trying to flow through this conductor, and the conductor is really, really thin, it's a very small, tiny wire, that wire is actually not going to be enough to allow all that electrical flow through it. And as a result, that electrical flow starts to slow down. It will resist current flow. Not all materials are great conductors of electricity. This is where another source of resistance can come from, and it's through other materials like silicon. And we looked at silicon as being this sort of semiconductor. It is this metalloid, this element that kind of has metallic and non-metallic properties. It's not really great at conducting electricity. It resists the flow of electricity compared to, say, something like copper or aluminum, these metals that we know are really good conductors of electricity. So sometimes just a simple material that is trying to allow current flow may just resist or slow down current flow. Now, in all of these different examples, whether they're loads or the types of material or the size, or if the gauge, what they call the gauge, or the thickness of a wire, if it's too thin, every time you resist current or electricity, you are going to get heat. That is a byproduct of resistance. When you resist electrical flow or current flow, you will get heat. Now, we can also measure resistance. Just like you can measure voltage or current flow, you can also measure resistance. And we use a unit called ohms, O-H-M-S, or singular is O-H-M. And that is the unit of resistance in electrical circuits. Now, when it comes to measuring the resistance in a circuit, we again have a specialized meter or a setting on a multimeter that measures resistance, and we call that an ohm meter. So there it is, resistance. It's analogy time for this one. I know we use the hockey sort of analogy to help explain current and all that kind of stuff. We're going to go back to those same concepts. We're going to use a different sort of analogy to help us, again, revisit stuff like voltage, current, and now resistance. And for this, we are going to go back to the land of Minecraft. All right. Hello, everybody, and welcome to the land of Minecraft. What you're looking at here is my fancy little contraption. It looks like a swimming pool, and it is, kind of. But you can see underneath it, I have this really weird sort of, here, let's just go down so you can see it. Underneath, if I were to show you underneath here, I've got these little trapdoors here. So at the flip of the switch, these things will sort of open up, and all the water in my swimming pool is going to come pouring down from here. And in fact, if you know anything from Minecraft, what I had to do is I created this so this is an endless supply of water here. So after I open this up, water will continue to pour out from this opening down here at the bottom, just so you know, all right? And the water in this analogy is kind of like the puck. The water here is going to represent the charges, the electrons. And right now they're not moving, so there's nothing really happening in terms of current electricity. But you'll notice if I sort of track down that I have this pool at a very high sort of height here. And you'll notice that this height, similar to what I did with the puck, is going to represent my voltage. So I've got a fairly sort of high voltage here because when I open up this door here, this trap door, and all this water comes pouring down, by the time this water travels down to here, it will have gained so much speed and it's going to hit here with a pretty good amount of energy. And like I said, that movement, these moving charges, is current. So I went for a high voltage and I've got a lot of current that will come down here and hit here. And so let's just see what happens when I do that, shall we? All right, and now I'm going to open these doors here and let's see what happens to those charges or the water. There it is. Down comes the water. There it is, and it hits there. Fantastic. Look at that. So again, just to recap, I have a fairly high voltage here because that is providing this potential energy for the electrons, in this case the water, to then sort of fall, and you can see the speed by the time it hits down here is quite high because I have a high voltage. So as a result, current flow has also increased. So the high voltage results in a high current flow, and that is what I'm seeing here. So this is part of that analogy. All right, next. All right, here we go. Here is a second pool that I've set up. Exact same sort of setup here. You can see underneath the water, I've got those trap doors again, and that is all connected to that switch way down there. All right. But you'll notice when I peel away from this and I start to sort of go down here, I've got these sort of things jutting out of the wall here. So the water will come down from there, but it will sort of hit these things on its way down. Now, you can kind of guess where I'm going with this. These sort of big columns, or whatever you want to call it, these arms sticking out of the wall, it's going to provide resistance. And as this current flow from the top here starts to come down here, these big arms are going to sort of hit up against the water as it's hitting and falling down, and it's going to slow down that water flow. And if this works, and I'll be really happy if it does, you should see the slowing down of current because of all of this resistance that we've set up here on this pathway, or whatever you want to call it, a circuit, if you will. All right, so let's take a look. And I'm going to sort of, let's try to set ourselves up so we can kind of see this like that. Oh, that's perfect. Look at this angle. And then I'm going to sort of raise this up and see what happens when it hits the ground. I may have to crane us around here. All right, so let's open it up. This switch will open up both doors at the exact same time, so the water or the charges will fall from the same height or the same voltage. The only difference is that we have resistance in this one example and no resistance here. All right, here we go. There they are. They are opening now. Let's see. Yes, yes. You noticed that the one that had resistance there hit the ground a little bit later, and that's because the current was slowed down because of this resistance that we have here. So that is a great analogy. I'm so happy that actually worked. Fantastic. And but it illustrates that resistance will slow down current flow. And don't forget, I'm using this analogy here of these big arms sticking out of the wall, but going back to our lesson, resistance is brought about because of loads being in a circuit. So if you had a light bulb, well, that light bulb is slowing down the current flow. Or if I have a motor it's part of the fan, the turning of that motor because of the electricity is slowing down the current flow. Or maybe I just have a piece of material like silicon in there, which is not so great at conducting electricity, so that is going to slow down current flow. Or maybe I have a wire that's far too small for the amount of current trying to pass through it. That's also going to slow down current flow. So all of those examples sort of apply to this analogy here. And don't forget, you don't see it, and then maybe it's not even happening, but as this current sort of hits this and gets resisted all the way down, heat is also being released from here. And that's the reason why the current slows down. Some of that energy in the current flow is being expelled off as heat energy as it's getting resisted. All right, so that's a fantastic analogy. Time to shut this off. How do I get down? Nope. This way, I guess. Hit the switch. Hit it. There we go. What are you looking at? Hello. I have no idea what you are. There it is. All right. Great work. We might come back here later. Sorry, I had to change. Put a sweater on. It's getting cold. It's like snowing outside. Anyway, so we're going to come back to those concepts of voltage, current, and resistance. But before we do, we have to also understand the different ways that we can connect stuff like batteries or loads. There are different ways of hooking them together or connecting them. And that's what we're going to talk about next. Parallel and series circuits. Now, again, you may already be familiar with these concepts. However, if you are not, I want to make sure you understand it. All right. What we mean by a series or parallel circuit. Well, series is really when we have loads or devices or power sources that are all on the same path, that they're connected together in the same path. Parallel circuits or parallel connections are when we have these devices or batteries or whatever connected so that they are on their own path, that they are not sharing the same path. They're actually found on different branches of a path. Okay, we've dealt with this kind of circuit before. Here we have two batteries in a row and three light bulbs or loads in a row here as well. Now we can actually attach some names to it in terms of how they are connected. These three light bulbs, in fact, you'll notice that if we were to take the path from the negative terminal here of this set of batteries and go through, we cut through one bulb, the second bulb, and the third bulb all the way back in and to the positive terminal to complete the circuit. We had to go through all three light bulbs, and it's because they are all on the same path. This makes it so that we can describe the connection between these light bulbs. We would say that they are connected in series, and this is a perfect example of a series circuit. In fact, the batteries themselves are connected in series because you'll notice here that the electron flow, and I know it's coming to the positive terminal here, but this, you cannot just pass through one battery and without passing through the next. Same thing here, you cannot pass through this light bulb without passing through the other ones. That means that they are all on the same path, and this would be an example of light bulbs connected in series as well as batteries connected in series. Let's take a look at what we mean by a parallel circuit. So in this particular circuit, we have three loads, in this case light bulbs, hooked up in parallel. And what do we mean by that? You'll notice that each of these light bulbs is actually on a separate arm or path in this circuit. We have our two batteries here providing the voltage and the current for our circuit. And you'll see that if we follow the path to one of these light bulbs and then back to the battery, that is its own path. You'll notice that we did not cut across or come into contact with any of the other light bulbs. This light bulb is really on a separate path than, say, this light bulb here and this light bulb here. Similarly, if we were to go to the second light bulb, let's start from here, we would bypass that connection there and go onto this branch and then back over and down to here. Again, we were able to get to the second light bulb and back to the battery without coming into contact or going through another light bulb. So again, this is also on a separate path, and we could do the same thing with the third light bulb here as well. This is a classic example or feature of devices, in this case light bulbs, being hooked up in parallel. This is what we call a parallel circuit or a parallel connection. These devices or these loads here are on separate branches of this circuit. Okay, so what the heck does that mean? Analogy time. All right, let's use this as an analogy, shall we? This is a map, and actually I needed a map with in a city that had fairly grid-like type of streets. So here's one of Toronto. The star down here is Union Station. It's the big train station in downtown Toronto, and you can see here we have 4 people that need to get to the train station. We have Connor, who's up at Toronto General, the hospital for sick children, that's where Braden works, and Mitchell, let's say Mitchell works at Google, and Una is there at City Hall. Or I should say Mitchell's at City Hall, Una works at Google. All right, so 4 different people need to get to the train station. And what we're going to do is we're going to use this analogy to show you the difference between a series sort of connections or series circuits and parallel circuits. So what we're going to do is we're going to imagine that we have here either a taxi or an Uber or whatever it is, a way for us to sort of pick up these 4 folks and get them to the train station. So the first way that we can do it, if we think of it, is we could then just sort of leave the train station and go and pick up Una over at Google, and then swing over to get Mitchell at Google, and then Braden's next, who's working at the hospital there for sick children, and then Connor working at Toronto General Hospital up there, and then back down to there. You can see we've completed like a circuit. And if we think of this sort of train station down here as being sort of like the battery, I guess you can think of, and these 4 spots here being the loads, you can see that this path that we took basically is one continuous path, and in that path we have connection to all 4 loads. This would be an example of a series pathway or a series circuit. And if we were to think of Connor, Braden, Mitchell, and Una as being loads, we would say that those 4 loads are connected in series, because again, there's only one path that connects all of them together. Well, what about a parallel circuit or parallel connections? Let's go back to the start again. So same scenario. We're down here at Union Station. We have our 4 people that need to be picked up from their respective workplaces, and let's get going here. So what we could then do is, well, let's send out a car, taxi or an Uber, out to go and pick up Una and bring him to the train station. At the same time, a second car can go out and pick up Mitchell and bring him back to the train station. And as that car goes, let's get a third one out to get Braden, and a 4th one out to get Connor. What we've now done is we've created essentially a parallel type of connection or a parallel circuit. Again, thinking of Connor, Braden, Mitchell, and Una as being loads in this circuit, and the star down here being sort of our power supply or our battery. You can see that Una, Mitchell, Braden, and Connor are each in their own sort of branch or circuit or pathway. When this taxi went out and grabbed Una, it sort of picked up Una and brought him back to the train station. Same thing with Mitchell. Picked up Mitchell and brought Mitchell back to the train station. At no point did the Uber or taxi pick up Una and then go pick up Mitchell. They were picked up separately, or they all had their own separate path around the circuit. That is a sign of a parallel type of connection. So again, Braden was picked up and Braden was brought back to the train station. Same thing with Connor. And as a result, this is a parallel type of connection that we're seeing here in this, I guess, make-believe circuit. So that's the difference between a series connection and a parallel type of connection. All right, so that is the end of the lesson. Now, for today's assignment, what we're going to do is revisit this concept of parallel and series circuits and have you investigate how that impacts stuff like current, voltage, and resistance. Now, you'll notice on this time around, I'm not going to be as structured. In fact, I'm hoping now that you've had enough time to play around with that little circuit builder simulator to start trying to conduct these experiments sort of on your own. I'll give you at least the circuit to start with, and then have you sort of go on from there. All right, take a look. We want to figure out how does how do series and parallel circuits impact stuff like voltage, current, and resistance. Good luck.